Okay, let me share my screen. Hello, everyone. My name is Peter Rose. I lead the Structural Bioinformatics Lab here at SDSC. And I've been using Jupyter Notebook for many projects over several years. And today I will talk about how to run Jupyter Notebooks anywhere. And what that mean on any platform, on your laptop, desktop, being a Mac, Linux, or Windows. And then also how to run that same code on Expanse. As your projects get larger, you may not have enough resource on your laptop or desktop. And I'll show you how to migrate over from that environment to Expanse. So today, we talk about first how to set up a reproducible and portable software environment where you take your software environment from your laptop or desktop and move it over to Expanse, and then also get the same reproducible results. Then I will go over a demo the Expanse portal. It's a web application that allows you to check your allocations on Expanse, check the status of jobs, as well as manage files from the portal directly. Then I'll show you how you run Jupyter Lab on Expanse. And one reason we want to go to Expanse is to scale up to larger data sets. So I'll show you an example using data frames, how we can scale them up using both on CPU and GPU cores. And then, as your calculations get longer, you may not want to wait for the results. You submit them in batch, and I can show you how to run Jupyter Notebook or Jupyter Lab in batch on Expanse. And then finally, most important for you, how to get ready to use Expanse. How do you apply for accounts on Expanse and allocation? Okay, so when do you want to run things on Expanse? First of all, your laptop or desktop is still the best environment for coding and the exploratory phase of your projects when you're still dealing with small data sets, where you run it on one core, on a few cores. One reason you want to use Expanse if you want to scale up either to larger data sets or runtimes becoming too long. In that case, you have now access to many cores on Expanse, or you can also use GPUs. So we can think about it this way. So on your laptop, you're in this lower green quadrant where, your task still fits into memory and the compute, is still reasonable. You don't need to run your laptop overnight to get your results. As compute resources increase, your compute bound, so it will take too long to run on your laptop. So that would be one use case, to use HPC system. The other one is if you don't have enough memory, or in most cases, you run into both limitations. This is a good use case using HPC systems such as Expanse. So let's talk a little bit about Expanse in terms of what's available. So Expanse has compute node, which are CPU nodes. Expanse has 728 nodes, and each of those nodes has 128 cores. So there are about 93,000 cores in total on Expanse. What's important is that each compute node has its own local storage. It has a high-performance solid-state drive. So a lot of the work you do or intermediate files you generate, ideally, you have those on this solid-state drive. And then we also have GPU nodes on Expanse, 52 GPU nodes. Each of those nodes has 4 NVIDIA V100 GPUs. And it also has 40 CPU cores on each node. And again, it has that local storage again, which we will be using. If you want to learn more about Expanse, please go to our user guide, which has much more information specific for Expanse. Okay, so when you run jobs on Expanse, you don't usually run them interactively, but they're running in the queuing system. We're using Slurm on Expanse, and you need to choose a partition or queue you want to run your jobs in. And here's a suggested partition or queue to run Jupyter Notebooks in if you're using CPUs. You can use the shared partition, and that allows you to run jobs on a single node using fewer than 128 cores. So this is usually a good choice for CPU-based applications. If you run a Jupyter Notebook that requires GPU shared is a good partition to use. Again, it runs on a single node with fewer than 4 GPUs. Now, sometimes you just want to do some quick testing or a quick run. In that case, you can use the debug or GPU debug partitions. They only allow you to run for 30 minutes, but they have a higher priority, so you will get your job running faster. So this is a good choice if you test things out. Use one of those 2 queues here. Okay, any questions so far?
No, none at this time.
All right, great. Okay,
There was one question in the chat.
Oh, okay, let me see here. The only one I see if the slides will be available. Yeah, they will be available after a while after the meeting, not directly, but yes. And the recording will also be available. Okay, let's talk about setting up a reproducible and portable software environments. And in particular, today I will talk about Python environments, since very frequently used. As you know, reproducibility is an issue. And that's not just true for bench experiments, but also, unfortunately, for computer code. I'm sure you have the experience that you try to run somebody else's code and you can't get it to work, or you don't get the same results. So we will try to address that issue. And here are some tools that help with reproducibility. So first of all, there's Jupyter Lab or Jupyter Notebook. And what's good about it, you can combine the documentation, the code, the results, everything, in a single environment. So that helps. Then, of course, we need to version our software. We can use Git to version control any changes in our code. And then we need a repository for our code, such as GitHub or GitLab, where you can, keep your code and share it with your coworkers or with everyone else. Now, to set up a reproducible software environment, there are 2 major choices you can use on Expanse. You can create a Conda environment, which I will talk in more detail very soon here. Or you can use containers, in particular Singularity containers. The difference with Singularity is that you not only package all the software, but also the operating system. So this is the best way to achieve reproducibility. But it's also more complex. So today I will talk about Conda and how to run that on Expanse. Okay, let's compare Conda versus a Singularity container. So Conda is best for beginning user, or if you already have some experience with Conda or pip installs, that's a good environment here. On the other hand, Singularity is probably best used by an advanced user, someone who has already experience, let's say, with Docker containers, or already experienced with Singularity containers. Conda environments are good if you do some exploratory environment. You don't know exactly what you want to achieve. You're exploring things. You go through various iterations. Your dependencies may frequently change, or you add new dependencies. On the other hand, Singularity is better used, to create a production environment. And for example, for Expanse, we have optimized container to run various machine learning packages such as PyTorch, TensorFlow, and so on. And they have been set up, for example, so they can run on multi-node, and they also take advantage of the high-speed networking available on Expanse. So Conda runs only on a single node on Expanse, so if you really want multi-node, probably Singularity containers is better here. Now, the good thing about Conda is it isn't supported on Linux, Mac, and Windows, so you can basically run it on any of your system, where Singularity only runs on Linux. And if you run Singularity on Mac or Windows, you would require to install some VM to run it on, because it needs Linux. And the good thing about Conda is it runs on your native operating system. Okay, but it's not an either or. You can initially start developing Conda environments, And then as you start productionizing it, that Conda environment can be included also in a Docker container. So it's not an either or, you can also use Conda environments within a container environment as well. Okay, so a little more about Conda. Why do we need Conda? When you try to reproduce somebody else's work, you usually have access to the code. In many cases, there's a paper available and hopefully also some data available. But the major reason why you cannot reproduce or run other people's code is because the environment is not defined very well or not defined at all. And Conda helps with setting up your software environment in a reproducible way. So what is Conda? First of all, it's a package management system that you use to install packages. I'm sure many of you have either used pip or Conda, to install packages such as NumPy, Pandas, etc. One thing that Conda does when you install any packages, it will also load any of their dependent packages, and it will also check compatibility in terms of version of those packages that you're installing. But it has a second function, and we'll use that today, and that's environment management. So you can create an environment on your local computer that uses a specific version of software that don't interfere with other versions. And then you can create an environment on one computer, like your laptop, and transfer it over to another environment like Expanse and run it there as well. So that's what I mean with portability. So as I said, it runs on multiple platforms, and it not only supports Python, but many other languages as well. So how do you create, or why would you use a Conda environment? What beginners typically do, they use either pip or Conda to install various packages. And if you have done that, you will notice after a while you run into, for example, version conflicts, you may run into errors, or you get non-reproducible results. The advantage of a Conda environment is that you can have different environments that use different versions of software, and they don't interfere with each other. So for example, this environment 1 uses Python 3.7 and particular version of Pandas and scikit-learn. You can have a second environment use a different version of the same software, and they can coexist. And you can use either one of the environments, and you won't have any version conflicts here. But more importantly, this Conda environment is portable. Let's say you work on a Mac, you can move it over to a Windows system or to a Linux system, such as Expanse. Okay, how do you define a Conda environment? It's typically done by creating a file that's called environment.yml. A good practice is to put this file in the top level of your Git repository, and this is the Git repository we will be using today. And if you go to this repository, you find this environment.yml file. First, it defines the name of the environment, and a good practice is to use the same name as your Git repository, so you don't need to remember the name of your environment. Then you need to define channels. Where do you download the packages from? And Conda Forge usually has the newer packages, and Anaconda, usually the packages are a little older. So that's why I put Conda Forge first to get the latest and greatest here. So the order of those channels matters. Then we define the dependencies, all the top level software packages that we require here. And you see I specify the version number here. Again, that's a good practice for reproducibility. It's also called pinning a version number. And as I said, Conda also allows you to install software, not just Python software, but other packages as well. So for today's demo, for example, we need Java. So here I also install Java version 17 as well. And this will not interfere with your current Java installation that you may have on your system. So you may already have, let's say, Java 11 or whatever version installed. This will not interfere with that. So that's another nice thing. Plus, you don't need to worry about how to install Java on different systems, Windows versus Mac versus Linux. There are differences. You don't need to worry about it. You just add that dependency here, and this Java 17 will be available for you. So then, in addition, you can also specify environment variables. So when you use this environment, it will apply those environment variables that will be available to you. So in this case, I set up some configuration for Spark, which is one of the packages to run in our code in parallel. So I'm setting up some configuration files and some memory configuration here. So again, for reproducibility reasons, I already include that here, so the user doesn't need to worry about setting those environment variables. Okay, then, now that we define the environment, how do you actually create it? So the first thing you need some Python environment. That could be Miniconda, which would be preferred because it's lightweight, but Anaconda 3 would also work well. If you need to install it, you can read up on this link here. So once you have Miniconda installed, then you can create a Conda environment by saying conda environment create -f, and then the name of this definition file, environment.yml. And if you have experience with Conda, you know that Conda is usually slow. Unfortunately, there's now an alternative here, which is called Mamba. So instead of Conda, you can also use Mamba. The command line looks exactly the same, but it's like 50 to 80% faster. And in today's demo, I will be using Mamba instead. So this is my recommendation. Try to use Mamba. It almost works in every case, and it's being much faster, uses less memory. After you create your environments, you can see what environments you created by saying conda and list. It will list all your current conda environments. And then now let's say I want to use a particular environment. You need to activate it. You say conda activate, and then the name of that environment, which is defined at the top level in this environment.yml file. And then you're ready to go. For example, let's say you want to run Jupyter Lab or Python, then you can do your work in that environment. Then when you're finished, you want to deactivate the environment. Now, this all works fine on Mac, Windows, Linux, on your local machines, but that's not the recommended way to do this on Expanse. The problem on Expanse is your home directory is on a network file system. So if you create a conda environment, it will be extremely slow, and so that's not recommended. So we make it easy for you in Expanse. We have a script called Galileo, which basically does all this for you in a way, that does not use the network file system, but instead it's running that on the local SSD drives. So our recommendation is don't do that on Expanse, but rather use this Galileo script, which I will introduce in a few minutes.
Peter?
Yeah, okay, that's a good time to
Yeah.
look at questions here.
Yeah, we do have a question in the chat.
Okay, all right, let's see. Yeah. Yeah, I'm not that familiar with PyTorch and its dependencies here, so I can't really answer that question. But one thing about Conda is that it can also be specific for a specific operating system. So for example, I will be using CUDA in the demo, and that is only available on Linux. You cannot run that on Mac or you cannot run it on a Mac, for example. So there are some limitations, So I don't know, Marty, are you online? Do you have perhaps an answer for that?
Yeah, I was just gonna respond. I mean, I can respond vocally. I mean, I would say in general, for this specific question, like if there's a sort of hard glibc dependency, that's usually pretty hard to get around. But if the individual has like specific questions, I would, I mean, a specific case here on Expanse, please send us an email and we'll try to figure it out. But yeah, it's very hard sometimes for certain things like this, that when you have a dependency on the operating system to get around. So,
and I guess that's why we're also using containers, let's say, for PySpark for more complex packages.
Yeah, that's probably the easiest solution. However, even then, that limits you to certain versions of operating systems in your container. So, but yeah, anyway, we haven't run into that issue for a while, but yeah, it can happen.
All right, thanks, Marty. All right, so now I want to introduce the Expanse portal, which is a web application. You can, check a number of things on Expanse. So the Expanse portal looks like that. It has various apps on it to check your job status, to look at your home directory, to open a shell, and so on. And to launch it, you can click on this URL. And what you need for it, you need to have your access credential. And I will talk about at the end of my talk how to get an access account. So for now, stay with me. So rather than logging into the portal now, I already logged into it. So let me just show you how the portal looks live. So this is the Expanse portal once you log in. Let's look at a few things here. So it's very convenient, rather than SSHing into the machine, you can just go directly here. So those are, all the files and directories in my account here. One nice thing about it is you can easily upload and download files from your laptop to Expanse and vice versa. So this comes in very handy. That makes file transfers much easier. Then the other thing is you need to run on Expanse, you need an account and you need an allocation. And you can see what your current allocation looks like by clicking here. So this is the Expanse allocation I'm using right now. Here's my username. Here's a project ID. And there are 5,000 CPU hours available, and I've used 3 of them. And we have separate accounting for GPU. So this is the GPU allocation, 250 hours of GPU, and I've used up 23 hours. So this is basically your bank account, your savings, and your checking account, where you can see where you stand with the allocations here. You can check your active jobs. And let's see. Thought I had a job running. I don't see it here. Anyway, your active jobs, they show up right here. And then you can also open a terminal shell by clicking on this. It's very convenient. So rather than SSHing into the machine, you can just click on that. And here I'm in my home directory on Expanse. So that was a quick tour going through the Expanse portal. And that's what I just showed you, looking for the CPU and GPU allocations, checking your job. So here's an example. Here you see this job was just completed. This job has been running like for 1 minute. And this is also a way to cancel any jobs. You can just click this delete icon to cancel any jobs. Okay, so how do you run? Next, we're going to talk about how do you run Jupyter Lab on Expanse. And let's see if there were any questions. Let's see.
Yes, there was one that came in.
Okay.
Peter. I'm just going to read it out loud for folks to know. If you manually install packages individually, do Conda environments create a .yml file with info on all the packages and environments set up, similar to the ones we have or we saw?
Yeah, it doesn't add it to the YML file. The YML file you create manually, if I understand your questions correctly. But one thing you can do, you can list all the packages in your current environment, so that's why you know what's in there. So I'm not sure if I answer your questions. All right, then let me go on. So to run on Expanse, we're using a script called Galileo, and it allows you to launch Jupyter Notebooks or Jupyter Lab on HPC system. As you probably know, if you run Jupyter Lab on your laptop or desktop, it uses HTTP, which is not a secure connection. And on our supercomputer, it needs to be secure. So it needs to run through HTTPS, and Galileo sets up a secure connection between the notebook server and the web browser. There's detailed documentation available at this link here, and Marty had a nice webinar, so you can also look at this recorded webinar to learn more about Galileo. So how do you use Galileo? So first of all, you need to set the path to Galileo, and this is the path you want to set. To make it easy, you may want to add this path in your .bash profile file, which is on your home directory. That way you don't need to set that path every time. So how do you launch a little notebook with Galileo? You say Galileo launch. And now you need to provide some information. First of all, you need an account on Expand. So you need to say, okay, what account number will I be using for this run? Then you need to say which partition or queue are we using. Remember, there were different queues there, like shared, GPU shared, debug, and so on. So for example, here, I use the shared partition, which means it's a CPU partition on one node, and you can use up less than 128 cores for that. In this case, I request 10 cores and 20 gigabytes of memory. And then you need to specify a time limit. So a time limit I've set here for 30 minutes. And here is where the Conda environment comes in. First, you specify the name of the Conda environment, which is in this case DF parallel. And then you need to specify the location of that YML file that contains the definition of your Conda environment. And once you run that, Galileo will print a URL on the command line. So you can copy this URL, you paste it in your web browser, and that's the way you access your Jupyter Notebook. Okay, so what happens once you paste that URL into a web browser? It will set up a job. First, it queues the job, goes through several stages, and once those 4 icons are all green, then Jupyter Lab launches on your web browser, and you see this is the URL that you originally pasted into your web browser. Then you do your work in Jupyter Lab. But important thing is when you are finished, don't just exit the browser, but go to the file menu and click shutdown, because that will terminate the process. If you don't do that, the process will keep running until it reaches its time limit. So you're wasting your resources if you don't shut it down, because the process will keep running. Okay, any questions about running Jupyter Lab using this Galileo script? Let's see. Okay. So let's see. Yeah, so I guess Isaac, he actually tried to run things using Galileo and it got some problem here. Maybe we can talk about that offline, since that's very specific for your case here. Let's see here. What is the recommend to use software that cannot be installed with Conda? Yeah, I guess that depends what it is. If you have other packages that are only available in pip, you could still use pip install as well. But I'm not sure if you may talk about various other packages. Otherwise, if you have a problem installing any software on Expanse, you can contact our help desk and they can also help you with that. You don't have root access, so that may limit what you can install. Not sure I answered your question. All right, let's go on. So, one reason we want to use Expanse to scale up, to larger data sets or more compute-intensive tasks. And we will look at 2 cases, scaling up on CPU and scaling up on GPU. And the use case I selected here are data frames. If you're using Jupyter Notebook, most likely you have used or may use, pandas data frames. And how can we scale that up? So in case you're not familiar with pandas data frames, pandas is a library that reads basically tabular data that can be CSV files, TSV files, or JSON files that have some tabular structure. And then you can manipulate data like you would do similar to in a relational database. But let's say your data set is large. Let's say the memory required to load your data frame is this much, but the memory available is just this much. So you don't have enough memory. So this is kind of a memory bound process. So instead of pandas, we can use a Dask data frame. So what Dask does, it basically breaks up this data set into what is called partitions, where each partition is again a pandas data frame. So basically it breaks it up into multiple smaller pandas data frames. That way you can process, any large data set, doesn't matter how large it is. This is also called out of core. So if your data don't fit into memory, that's usually referred to as out of core. So that allows you to run very large data sets. Now, one advantage of splitting this up is also that you can now run things in parallel. You can run those partitions in parallel, and I'll show you how to do that. So the Dask looks very similar to the pandas data API, but there's some slight difference, and it only supports a subset. But it's very similar, as you will see in my example. So this is one way you can process very large data sets in parallel on Expanse using Dask, and I will show you an example later. The other way to do that is to use a GPU-powered data frame. So NVIDIA has a set of tools. It's called the Rapids AI, which are basically GPU-powered tools for data science, and they developed a library called CUDA-DF, which is a GPU-powered data frame, which looks very similar to pandas. It has most of the pandas functionality, but it has the same problem. If your data frame does not fit into the GPU memory, you still run out of memory. Again, this is where Dask comes to the rescue. There's also Dask CUDA-DF, which again splits up the data frame in multiple partitions, where each partition is again a CUDA data frame that runs, you can run out of core data sets, but now those partitions are run on GPU rather than CPU. And again, Dask CUDA-DF only supports a subset of the pandas API, but most of the functionality is there. Okay, so here we will be running now a few example notebooks to demonstrate that, but let's first look at the different notebooks we're looking at. So first of all, we look at the pandas library that I'm sure you're familiar with. It runs on a single core, it doesn't run parallel, and everything needs to fit into memory. So that's why I said out of core. No, it will run out of memory if the data set is too large. It runs on CPU. Then we will look at Dask, which allows you to run in parallel. And since it splits up data sets, it won't run out of memory. Again, it runs on CPU. One package I haven't mentioned yet is Spark. Spark is similar to Dask. It allows parallelization of data, but it's not a Python package. It's written in Scala. It runs on the Java virtual machine. But there's a Python wrapper called PySpark, and that's what we're going to be using. Again, it runs in parallel and it splits data set up into smaller partitions. So you don't have a problem with running out of memory. Then we're looking at GPU-powered data frame. CUDA-DF, again, runs in parallel on this GPU, but again, it will run out of memory. And then lastly, we look at Dask CUDA-DF, which has the best of both worlds. It runs in parallel on GPU and it doesn't run out of memory. Okay, so how do we run those examples on Expanse? So we're using this Git repository. So you would first clone this Git repository, and then to run the GPU-based data frames like Pandas, Dask, and Spark, the command line would look like this. You launch Galileo, account number, the shared partition, 10 CPUs, 20 gigabytes of memory, 30 minutes time limit. And as I showed you before, the name of the environment and the path to the environment. And finally, we add the option -member, which I explained before. This will make building the Conda environment faster. So I suggest you add the member here. Now, if you run on GPU, command line looks very similar. The only difference is here we use a GPU shared partition. We request one GPU here. And now we're using a different environment, the DF parallel GPU environment, which has additional dependencies on Conda, on CUDA, for example. All right, so that's the only difference here. Okay, so now we're going to do a demo. So this is what we're going to run in the demo here. We're going to run it on a GPU partition here. So the way that works is, I'm going to copy this command line here, and then we're going to expands, and we're going to the command line shell, and we paste this here. So once you paste that here, it starts a session, and let me show you that. So it repeats, your input parameters, but at the bottom here, there's a link here. So you copy this link and paste that into your web browser. And I'm not going to do that right now since I already have something running here, but just show you how it runs. So once you do that, it will go through its stages. It may take a few minutes, and then Jupyter comes up. Unfortunately, my version I launched earlier exited for some reason. I don't know why. Anyway, so unfortunately, we need to wait until, actually, I need to paste it in here. So let's see. Maybe I didn't copy this right. Move that out of the way. Oh, there we go. So it first needs to get in a queue. Unfortunately, it's going to take a few minutes now since I didn't realize my previous job had already finished. So unfortunately, I need to start it again here. But this will be now a good time to take some questions. Let's see. Right, let's see here.
Hey,
Mark,
Peter, I have a question. Is it okay to ask?
Yeah, sure. Go ahead.
Okay, yeah, this is Brian Jester. Hey, so it looks like I basically submit my job, but I may be waiting to see the results. So if I actually forgot about it and came back to it a couple days later, would my results still be there?
Yeah, I'll talk about it. So what we're doing right now is we are now running Jupyter Notebook interactively. So you always need to save your results yourself since it's an interactive session. Later on, I'll talk about how to run Jupyter Lab in batch. And then obviously you need to save your data, and we'll show you how that works. So I'll talk about that later. So I'm not sure if that's
Yeah, that makes sense. If I'm running it interactively, I'm using it, I'm watching it run. And
Yeah,
then
right.
if I've submitted something, maybe I'd save it in my home directory or somewhere.
Yeah, right,
that I
right.
was
Somehow you
recovering.
need to, save your results, right?
Right. Gotcha.
Yeah, and I will show you later in terms of a batch run and how you could save like a Jupyter notebook. So yeah, that's a good question. All right.
Peter, I can
other-
read the questions for you.
Yes.
Yeah, so there's one asking, can we use Dask to do ML calculations to parallel it?
Yeah, Dask is a little limited. So Dask has some libraries that work together with scikit-learn, for example. So there are some use cases where you can parallelize some scikit-learn machine learning. So for example, if you do a grid search for machine learning, that would be an example where you could use Dask, for example, to parallelize a grid search. And again, I think it's using both scikit-learn and XBoost. Those are two of them, but it's rather limited what you can do in terms of task and machine learning.
Thanks. Hope that answered your question. The next one, Marty already responded, but I will just ask it for recording purposes. Using Jupyter Notebook, can we use multiple nodes on Expanse? The response was, yes, you can request multiple compute nodes for your Jupyter session. And the last one is really, could you copy and paste your demo command into the chat, Peter?
Yeah, sure. Let's see. I think it should be still there. Let's see. But we will be sharing the slides and everything is also in this Git repository. Let's see. Oh, that's not the right one. Okay, let me go back here. I'll paste that command. Just 1 second. All right. Okay. Okay, so maybe that if there are no other questions, are there any other questions, Cindy?
No, and not at this time.
Okay, so let's then look. You see, Jupyter Notebook came up, and it takes a few minutes for it to come up, since first it needs to get into a queue, then it will build that Conda environment, and that Conda environment I have here is very heavy. It has Spark in it, it has CUDA in it, and so forth. So this is a very expensive environment to build. So first we need a data set. So I have a notebook here called download data. Let me run this first. So this will download a file that's about 6.4 gigabytes. And what it has a list of genes and annotations. This file comes from the NIH, from the NCBI. So it has some information about genes in it. So this is not a real big data set. So I picked one that's kind of small, so it doesn't take too long. So we download this data set. And by the way, one thing I mentioned earlier, if my title is Run Jupyter Notebooks Anywhere. So if you download data, if you're on Linux, most likely you would put a wget command in here to download this particular file here. But what I've done here, I'm doing this all in Python. So to download the file, I have some code here, and also to unzip the file. I don't use the command line tools. The advantage of that is this will run also on Windows and Mac and so forth. So if you really want to be run anywhere, I suggest using those methods. Again, we share this Git repository with you, so you can copy that in case you want this functionality. So I'm avoiding to use command line tools, so it runs really everywhere. So we just downloaded this file. It's 6.4 gigabytes. And let's do some manipulations on it. So first, we're going to use a pandas data frame to read in this data set, plus do a few manipulation on this. So let me run this. And then I explain to you what it does. So I mentioned that each node has a local solid state drive. And to access it, there's an environment variable. When you run that Galileo script, it sets an environment variable called local scratch dir. So I'll be using that. So anytime you have large files or you create large intermediate files, be good practice to put them onto that local scratch drive. You basically move the data where the compute is. So we're using this local scratch directory where we keep the files. Then we're using pandas to read the file. So this file has multiple columns, and here I specify just a subset. I don't want to read all of them. And then we finally read that information. So in this line, we're using the pandas data frame to read this file, this specific columns only. And it's actually not a CSV file, it's a TSV file. So that's why we put this tab separator here. And then once we read the data set, we filter it. We say, okay, we only want those genes that are protein coding. So I reduce the size of this data set by this query here. So this data set, while it's 6.4 gigabytes on disk, when you actually load it into memory, it actually takes up about almost 18 gigabytes because Python objects are very large. So this is a top view of this data set here. So it has some gene information in here. So one thing we want to do here, and this is just to exercise a few commands here, want to group by what's called this taxonomy ID. Each taxonomy ID corresponds to some organism like human or mouse. We want to know how many genes belong to each taxonomy ID. To do that, we run this group by command first to count how many genes belong to each taxonomy ID. And finally, we sort those groupings as descending. And then we print out some results. So how many human genes are there? There are like about 20,000. And since we sorted that descending, you can see the organism that has the most genes is this one with 104,000 genes. I don't want to go into the biology here. What really matters is this number at the end. That took about 67 seconds on pandas to run. Now let's do the same thing with Dask. So let me close this. And let's run exactly the same data analysis using Dask. It's pretty much all the same thing. So you see in the import statement up here that I import a Dask data frame as DD. So when we then read the file, instead of PD for pandas, we use DD for the Dask data frame. Otherwise, the syntax is the same. And again, we group by, we sort by values. One thing that's different with Dask is kind of works in a declarative way to tell it what to do, but it does it all lazily. It only starts the calculation when you say, for example, .compute. In that case, it will actually do the work. And okay, and then the results are exactly the same as before, but now it took like 19 seconds. So it was about 3 to 3.5 times faster, because what Dask did, it read this data set in parallel and processed it in parallel on CPU. So we gained about a factor of 3.5 here running this with Dask. Okay, now let's look at a Spark data frame. So Spark is very similar to Dask, except it runs on the Java virtual machine, but it has a Python wrapper called PySpark. So I'll run this one. And the syntax for the API is quite different, but the idea is the same. It's a little bit more complicated. You need to set up first a Spark session here. And then finally, you read the CSV file. Again, the syntax is different, but the idea is the same. And then we select specific columns here. We filter by the type of gene. And again, we group by taxonomy ID and sort it. And then we show the results again, identical to what we had before. It took about 14.7 seconds. That's about 4.5 times faster than pandas. Okay, now let's move on to GPU. Now I'm running this on a GPU partition, so we can run this also on GPU now using a CUDA data frame. So let me run this now. So instead of using pandas, we now use importing CUDF, the CUDA data frame here. And I added this NVIDIA.SMI command in here that shows you some information about the GPU we are using. We're using a Tesla V100 GPU. And one reason to want to print this is because it tells you what the driver version number is. When you create your Conda environment, you need to specify a particular version of the CUDA libraries, and that needs to be compatible with this driver version here. So that's one reason I'm using that here. Okay, otherwise the code basically looks exactly the same as before. Instead of pandas or Dask, we use now CUDA-DF, but you see otherwise it's identical. And then we do the same thing. We group by, we sort. The results are again identical. And this was much faster, so it's 3.8 seconds. This is about 18 times faster in this case as using pandas. So, the GPU is not just fast in terms of processing the data, it's also very fast accessing the data from that solid state drive. So, there are two factors that really make it this fast. Now, this data set was small, so I said in memory, it's about 18 gigabytes. So that fits into the NVIDIA GPU memory. So the V100 GPU we are using has 32 gigabytes of memory. So it fits, it's no problem. But if we have larger data sets, it will run out of memory. In that case, we would use Dask CUDA-DF, which again, splits the data frame into multiple CUDA data frames. And let's run this one. Isn't necessary in this case since we're not, running out of memory, but I just want to show you how it works. Basically, everything is identical as before. Now we're using the Dask CUDA-DF to read that file. Otherwise, everything else is identical. Now, it took a little longer, 8.7 seconds. That's because now you're splitting up that data set and running it in parallel. So there's some overhead involved. In this case, obviously, it was a small file. It doesn't make sense. But if you run larger files, then you will see then you will actually gain by using a Dask. So, okay, that's the end of my demo. Before we end here, let's look at a few things. Let's look at the dashboard here and look at our active jobs first. So this is that job that I'm just running here, and it has been running for 14 minutes so far. And okay, back to here. So one important thing is when you're finished, you don't just close the browser, but actually go here and go to shut down your Jupyter Notebook, and that will terminate the process. So let's see if we go back. Okay, now we can close that window here. And now let's go back here. Unfortunately, this does not update by itself. You need to rerun this again. And now you see, the job has now completed. But let's say you forgot to shut down Jupyter, under the actions, there will be a cancel button. You can cancel your job here as well. All right, so back to my presentation here. Yeah, let's say this might be a good point to take some more questions then. Okay, let's see.
Yeah, Peter, there's one that I will bring up here. When preparing notebooks, do you write them locally, then upload them, or do you launch blank notebooks, then write the code?
Yeah, I mean, I can talk about what I do. I usually develop my notebooks first on my laptop and then transfer it over to Expanse. But there's no reason you could do the same on Expanse too. You could write your notebook there too and then save it. So the way I do it, I develop my notebooks on my laptop, and I put all those notebooks into a Git repository, including the Conda environment, the environment.yml file. Then I go to Expanse and I clone the environment there, and and then use Galileo to run it. That's my typical workflow, because editing on Expanse, let's say you requested 10 cores. If you just do editing every hour, you burn up 10 hours of your allocation. So it's better to, as much as possible, do your editing somewhere else. So hope that answers the question.
And then there's one last one that came in. What happens if you click the Jupyter button on the main Expanse portal page?
Yeah, so you can also run Jupyter Lab out from the portal itself, and in the background it will run Galileo. In that case, you need to fill in, the name of the Conda environment and things like that manually. But it has some limitations, and that's why I'm showing you today how to run this from the command line using Galileo. But in principle, you can do that. So the problem is that the current Jupyter Lab application or Jupyter app on the Expanse portal has some limitations. So it's still a work in progress. It doesn't have all the functionality. That's why I was using it on a command line. But one advantage of doing it like I did here is that you can save this launch command, and every time you want to launch it again, you just reuse it. You don't need to set up all the parameters. You may forget about what partition you use and so on. So that's one advantage of actually using the Galileo command line rather than the Expanse portal app. So, all right. Okay, any other questions? Okay, if not, let's see how we're in time. Okay, I need to get going. All right. So here's a comparison. Now, today we had a small data set. So I ran this a year ago, and the data set was 5.4 gigabytes. Today it was 6.5 gigabytes. And here you see the runtime. It's about what we just saw during our demo here. Now what I did then to increase it, I made another data set, which is 4 times the size, which is this one here. So pandas still work because the data set was 62 gigabytes in pandas and we requested 92 gigabytes of memory. So it still fits in memory. Dask and Spark are faster as expected. And then CUDA-DF ran out of memory because the V100 GPU has only 32 gigabytes of memory, so that won't fit. So get out of memory error. But Dask CUDA-DF works. And I create another data set, which is 8 times the size. On disk, it's 43 gigabytes. In memory, it's about 120 gigabytes. Now, in this case, now Pandas runs out of memory. But as you see, Dask and Spark works well. Basically, CUDA runs out of memory. And in the Dask, CUDA-DF worked as well, yeah. So here you see now what happens if you run, actually larger data sets. Okay. All right, how do you run JupyterLab in batch? Now if you really scale it up, you don't want to sit there and run your JupyterLab. You just want to start it and let it run and you do some other work. And you can do that using a library called Papermill. It allows you to parameterize notebooks. And what that means is you can pass in arguments to do a Jupyter notebook. And then it can also execute notebooks. And here's an example of a piece of a shell script to execute a Jupyter notebook. In this shell bash command, you say you loop over your notebook files and you say Papermill. This is your input notebook, $F. And then you need to put the results somewhere. That was a question earlier. I create this results directory and the executed notebook will be saved in this results directory. So it's basically the same as the input notebook, except it has all your calculations, all your graphs, whatever you did in your notebook will be saved and you can get back later and look at your results. So here's an example script how to run that. So if you ever need to run it, you can use this as an example. It's in this DF parallel Git repository. Once we post the slides, you will have access to that. So in here, you need to specify all the commands that you saw on the Galileo. Now, what's the account number? Time limit in this case was 8 hours. Which partition? How many nodes? How many GPUs? How much memory? And so on. I won't go through all the details here, but you can use it as a template. So if you want to run JupyterLab in batch on Expanse, have a look at this file. And at the end, you see I'm using Papermill to run Jupyter Notebook. For example, here I say run this 7 parallel efficiency notebook and save the results in this notebook. And then I specify parameters. How many cores do you want to use? What file format want to use? And what kind of data frame you want to use? Those are parameters passed into the notebook then. All right, I think we are getting short on time. So let me go on. And to submit a job, you say as batch and then the name of that job script like this one here. Okay. Okay, so now the final step is, if you don't have access to Expanse yet, how do you get allocation and accounts? So if you want to just start out to try something out, you can ask for a trial account, and there you will get 100 GPU hours and or 1,000 CPU hours. And to do that, send an email to consult@sdsc.edu. If you apply for a larger allocation, you need to go to what's called the access system here, and there are different levels of allocations you can get. They have different names. Here's a little description, and I don't have time to go through that, but obviously, the Explore level is, for initial evaluation, small student projects, small classes. Then the Discover allocation is, if you do larger classes, training sessions, or you do some benchmarking and testing at scale. And then if you get to larger, projects, you go to the Accelerate project. And if you have something super large, you can ask for a Maximize allocation. So in summary, I showed you how to create a portable and reproducible software environment, how you use the portal, how to run JupyterLab on Expanse. Then I showed an example of data frames, how they can be scaled up using on GPU and CPU, how to run JupyterLab and badge, and finally how to get an allocation on expense. And then I want to acknowledge my co-workers here, Marty, Mary, Robert, and Scott. And finally, this effort was funded by the NSF through a cyber training grant. Okay, any questions?